This episode, I got to speak to cosmologist Dr Eva-Maria Mueller about the Big Bang, the expansion of the universe, and the mysterious accelerating force known as dark energy.
My name is Eva-Maria Mueller, and I'm a researcher at the University of Portsmouth. I'm a cosmologist, and I'm in particular interested in studying dark energy and studying the expansion of our universe.
That's pretty cool. It's no small task.
No.
Thanks very much for coming on the podcast, Eva. Now, the reason we're speaking is because you're one of the 10 sort of new scientists who've been selected for the Ernest Rutherford Fellowship at the Science Technology Facilities Council. I thought it'd be worth kicking off just talking a bit about that, exactly what it is and how you came to be involved.
Yeah, so the fellowship is a 5-year fellowship. It's a research fellowship for various different topics. So for me, within the field of astrophysics and astronomy. And that fellowship really allows me to conduct my research freely for the next 5 years and independently. So these Ernest Rutherford Fellowships here in UK, I think one of the top methods of actually getting a permanent position and becoming a professor. So these fellowships are really a gateway to a tenured position in academia. And so I think it's what a lot of postdocs and PhD students is thriving towards. So having a career in research, having a career in academia and science. So I was very happy when I got this fellowship because it felt like, the struggle of only like fixed term contracts for 2 or 3 years now is finally over, and I can concentrate on just doing my research and not worry about anything else.
That's pretty cool. And as you said, your research is about, the expansion of the universe, but not just the expansion of the universe, the fact that the expansion of the universe is accelerating and how we sort of deal with that quandary, I suppose. What attracted you to this subject? Because it must just be absolutely daunting.
Well, I was always fascinated by astronomy and astrophysics from a very young age. And then I was very good in science in school, so I decided to study physics. And then within physics, I chose to elect astronomy and astrophysics classes because I was just very fascinated by that. And then started my PhD. I went to the US, so I went to Cornell University. And then one of the professors there, Rachel Bean, was working in cosmology and on the cosmic microwave background. And, she gave talks and I found it all very fascinating. So I decided to go into that field. And for me personally, I also like a bit of the balance between doing theoretical work, but then also having data to analyze and, going to a telescope and observe for a couple of days. So you have like, I think, the best of both worlds of being a theorist and being more of an astronomer.
Yeah, that's pretty awesome. I mean, because there's sort of this notion sometimes that maybe astronomers nowadays don't actually sit at the telescope, that it's a lot of sort of analyzing data and looking at computer screens, but you still actually have time to actually observe the night sky?
Not very often. So I was very lucky a couple of years back where I went to Chile to observe. And but we're not really doing it on a regular basis. In particular, what I do, it's a group effort, so it's a large collaboration. So I currently work with the Dark Energy Spectroscopic Instrument. And we're over 500 people. So overall, that only means that you get to observe maybe once or twice per year if you're lucky. And that was before the pandemic. Since the pandemic, they actually changed it all completely to remote observing. So now it's really mainly sitting in front of your laptop. Unless you're one of the lucky ones that are actually, operating the telescope in Arizona at Kitt Peak.
Awesome. Before we sort of get on to dark energy and the expansion of the universe. I did want to see if we could go sort of all the way back to the start of the story. How close does our knowledge of the universe get to the Big Bang? Just how far back do we understand what was going on at that time?
I would say pretty far. So now just to step back, we believe the universe in the beginning was very hot, very compact and very dense. And then it started to expand and to cool down. And as it cools down, you have the first atoms formed, you have the first hydrogen formed. And then these hydrogen they're gravitationally attracted, so they start to clump. And over time, you have the first stars and galaxies formed. And then also first planets and life on Earth, etc. So it's really up to like a fraction after the Big Bang, where we might not know all of the puzzles, but I think we have the broad picture of what is going on. But if you really ask me what is happening at the Big Bang, that is much more difficult, because at the Big Bang, it's what we call a singularity. And at that point, really, our laws of physics break down. So the conditions are just so extreme that we just cannot apply the normal theory of gravity anymore. What we really need is a unifying theory of quantum mechanics and gravity, and that doesn't exist yet. So there's really completely where our knowledge breaks down. But even after, a fraction of a second after the Big Bang, there's something that we call inflation. So extremely rapid exponential expansion of our universe. And it's postulated that it's there because it allows us to explain certain effects in the universe. But the underlying mechanics, we still don't fully understand.
When you talk about the Big Bang as an event, most people will think, well, if it's an event, then there must have been something before the event. In your opinion, does it even make sense to sort of say before the Big Bang? Can you talk about before the Big Bang? And if so, do you think it's realistic that we could ever discover what happened before the Big Bang, or what came before the Big Bang?
So the Big Bang really is the start of everything. It's the start of time itself. It's the start of space itself, and combined what we call space-time. So in that sense, the question becomes a bit, well, what does it even mean? If there's nothing, what was before the nothing? There are a few, theories of bouncing cosmologies, where you would have an endless Big Bang, expansion, contraction, next Big Bang, and so on. But yeah, for me as a physicist, I study the things I want to explain, what I can see. So for me, the question, what's before the Big Bang, is maybe more for philosophy than for physics.
Yeah, indeed. Well, let's move on to that then, because your work, as we said, is concerned with the expansion of the universe, and that's an interesting concept in itself, and that sort of raises a lot of issues, doesn't it, as well? First of all, how do we know that the universe is expanding, that it's still expanding?
So this really goes back to analyzing spectra. So when we get the light from galaxies, what we can do is we can break this light up into its components, into its different wavelengths. And when we go to our telescopes and observe the light of distant galaxies, what we will find is that all this light from galaxies is redshifted. So what that means is it's similar to the Doppler effect that in everyday life we know from a siren of a police car or an ambulance. So if the ambulance is coming towards you, then the sound is a higher pitch than when it's driving away from you, where it's a lower pitch. And it's not because the siren just makes different sounds when it comes towards you or further away. It just comes from the fact that the sound, the wavelength of the sound, is squeezed and stretched because of the motion of the ambulance relative to you. And now the same thing happens with the light from galaxies. We know what we would expect to see, but instead the position of these lines in the spectrum are either blue shifted, which would mean things are coming towards us, or red shifted, which would mean that the galaxies are moving away from us. And what we observe indeed is that all of these galaxies are redshifted, so all of these galaxies move away from us. And not only can we measure that they're moving away from us, but we can also measure how fast they're moving away from us. And so we are also seeing this accelerated expansion of the universe.
That's pretty. I mean, it's pretty mind blowing when you think about that. So it's essentially in the time that it takes from light from a distant galaxy to get to us, it's been stretched by the expansion of the universe. Have I got that right?
Yes, exactly. So space itself is getting bigger.
I suppose that brings us on to another sort of before the Big Bang type question, which is quite difficult to get your head around. But it's the notion that if the universe is infinite, how can it be expanding? You know, because how can it be expanding into nothing? Do you know what I mean?
Yeah, it's really hard to imagine that the universe started as something very compact and then started expanding. But it's not like it's expanding into anything. It's space itself that is expanding. And for a while, I mean, the Big Bang theory was not the only possible theory. People were thinking, okay, maybe the universe is static and infinite and has no beginning, has no end. But it was really the discovery, for example, of the cosmic microwave background that really gave proof of this scenario of a universe that has a beginning and then started to expand and started to cool down.
Let's move on to what you're going to be studying, because, I mean, dark energy is one of those concepts that's quite difficult for sort of regular folk like me to get my head around. Am I right in thinking that dark energy is the name that we give to the force that's causing the acceleration of the expansion of the universe?
Yeah, so you're not alone. Also, us astrophysicists are very puzzled as to why the universe is accelerating. So the way that I would describe it, if you think back to Newton and his apple, you know, the apple falls down. But imagine you throw up an apple or a ball, and instead of this apple coming down because of gravity, it just keeps flying away from you, and it keeps flying faster and faster away from you. And that is really in contradiction to what gravity would do, because gravity is an attractive force, so it would pull it back. But that is exactly what we see the universe is doing. And the only way we can explain this acceleration is by introducing this new form of energy, or dark energy. But it is really just an all-encompassing phrase for, we don't know what it is. We know that it's there. We know the effect that it has. But that's as much as we know so far. So dark really here is partially a lot our knowledge about the subject is very thin.
And isn't it the case that sort of dark energy and then also dark matter, that's the majority of the universe, isn't it?
Yeah, exactly. So we know that dark energy is about 70% of our universe, and the rest, 28%, is mainly dark matter. And the rest is baryons, you know, the stuff that you and me are made out of. And then also we have light, so we have radiation from galaxies and stars and so on. But the majority of our universe consists of that thing we basically I have no understanding whatsoever.
So how is your work actually going to look at the mystery of dark energy and potentially solve the mystery?
So for dark energy, from a theoretical perspective, there are different options of what it could be. So one of the simplest explanation would be that dark energy is just a cosmological constant. So mathematically speaking, it's a constant that you can introduce into our equations to kind of balance the scales, if you will. And the way to interpret this cosmological constant is as a vacuum energy of space itself. Ground zero energy, that's just intrinsic property of space. The problem with that really is that we can also, from a theoretical perspective, we can calculate what that should be. And we are several orders of magnitude off between this theoretical prediction and the actual observation of the energy density, of the dark energy density in our universe. So that's why it's just a constant is a bit problematic. However, what we can do is we can measure how the universe is expanding over time. And we can see if this acceleration is driven by something constant, like a cosmological constant, or if it's also evolving over time. So one other possibility would be that it's just a new form of energy. So something that only interacts gravitationally, that's why, and because it's very low density, we haven't really observed here on Earth in our everyday life. But that is actually a new form of energy. And that could have the possibility that it's not a constant, but that the acceleration evolves over time, that it's like it's becoming faster, slower, and things like that. So this is one of the key observations that we're really trying to test. So it's something called the dark energy equation of state. So that basically is, how does dark energy affect the expansion of our universe over time? And lastly, also a third very exciting possibility is that actually our equations are wrong. So it's not that we actually have this new form of energy, but Einstein's theory of relativity basically gives you an equation for the dynamics of the universe on the one hand and all the energy in the universe on the other hand. And of course, we want the left-hand side balanced to the right-hand side. And that's why, because of this matching the balance, we introduced this constant or dark energy. But it could also be that just, the equations are wrong and that we need to modify general relativity or have some form of general relativity if we talk about the universe as a whole. And then that we can also observe by looking at the growth of structure in our universe and how it evolves over time. So specifically, what I'm doing is I'm really interested in creating a three-dimensional map of a distribution of galaxies. So what I mean by that is we're going to observe millions of galaxies, and we're going to look at where is it on the sky, so its angular position. But then also we measure its redshift, which gives us its distance. So like that, we really get a three-dimensional map of the distribution of galaxies in our universe. And then we can basically slice through that in like steps of distance, which is equivalent to different eras in the history of our universe, and then see how the universe expanded. Is it going faster? Is it slowing down? And so forth. And specifically what we're using there is something called baryon acoustic oscillations. So it's a very nice technique that is basically in the very early universe, you have these acoustic waves, like sound waves, and these imprint rings in the distribution of galaxies, and that we can still measure today. So in this distribution of galaxies on the sky, it's not completely random. You have like hidden patterns in this distribution. And what I'm trying to do is measuring this hidden scale, this baryon acoustic scale, in what we call the large-scale structure of our universe. And then this scale, as I said, we can measure the scale at different times during the history of our universe. And because we know how big the scale is expected, we can compare it to our measurement and like that gain information how the universe expanded and then constrain the acceleration of the universe, and by that constraining the properties of dark energy.
It just sounds like such a mind-blowingly mammoth task. Do you sort of have a prediction as to how long the project will take?
So for my current project, analyzing data from it's called DESI, the Dark Energy Spectroscopic Instrument. So this is a 5-year survey. So for 5 years, we're gonna scan the night sky, getting spectra of millions of galaxies, and then analyzing the data. And that really will give us percent level precision on the expansion of our universe up to a redshift of 3.5. So see, in cosmology, we always describe distances with redshift, so much so that in my head, I'm not thinking, in light years or in these other astronomical units. For me, the history of the universe is always in redshifts. So redshift of 0 means it's today. And the higher the redshift, the further back in time you go. So approximately at 0.4 and redshift of 0.4, the universe started to be dark energy dominated, where the expansion is really driven by this dark energy component. And if we go back further in time, there was a matter-dominated era where the expansion was driven by the matter content of our universe, so by the dark matter. And then if you go even further back, it's the so-called radiation-dominated era, where photons were driving the expansion of our universe.
Well, that's a really interesting point. That's something I've never thought about before. So, do we know that? Can we say to a certain degree of certainty that dark energy wasn't always there?
Dark energy was there, as far as we know. It is just that the overall energy of our universe was dominated not by dark energy, but by matter. But as the universe expands further and further, and all the galaxies are further apart, that eventually the driving force really is being taken over by dark energy. So the acceleration or the expansion of a universe then is dominated by that form of energy. So you can think about it in the early universe where everything was very hot. There the dominant energy was from radiation. But as then the universe expands and gets cooler, that eventually turns into an era we call matter-dominated era, and then eventually dark energy-dominated era, which is the era we are currently in.
It's like you're traveling back in time. That always really fascinates me about the work of astronomers and cosmologists like yourself. It's this idea that you're sort of almost looking back in time. It's pretty cool, isn't it?
Yeah, it is, and it's coming from the fact that the light from distant galaxies just takes so long to reach us. So by the time that star that we observe might not even exist anymore.
Yeah, it's sort of done us a favor, hasn't it? The speed of light has sort of done us a favor because it takes so long that we had the time to evolve as a species and invent telescopes and, and, gravitational wave surveys so that we can actually observe the early universe.
Yeah. It also goes both ways, right? If you think of someone else far off our galaxy observing this little light that comes from Earth or from our star.
Yeah, it's pretty mind-blowing. The other thing that really interests me about the notion of dark energy is it's sort of sort of changed our view of the future of the universe, hasn't it? Because I remember being in as a sort of young teenager being in physics class, and at that time, this is probably showing how my age, but at that time, the idea, it was pretty certain that the expansion of the universe would slow down and eventually reverse and can contract into like a big crunch. But that's obviously not the case now that we know about dark energy accelerating the expansion of the universe. So it's really interesting how the discovery of dark energy it's actually changed our view on how the future of the universe will play out, hasn't it?
Yeah, even though I would say, because we still don't know exactly what dark energy is, we could be in for a surprise. So yes, if dark energy behaves like a constant and also in the future will behave like a constant, then the most likely scenario is that of a so-called freeze out. So what I mean by that is that the expansion continues and all the stars and galaxies around us will get further and further away from us. So the light will get more and more redshifted, it will get more and more dimmer. So the universe as a whole keeps continuing to cool down, and eventually everything will be dark. Also, the stars will start running out of fuel, so they will slowly die and then end up, in a supernova, as a white dwarf, as a neutron star, as a black hole. But even black holes eventually, through Hawking radiation, will disappear, and we just end up with this freezing, dead universe. But I mean, who knows? Who knows? Since we don't know what dark energy is, if dark energy has like peculiar behavior in the future, that could also be completely different and going back to a big crunch scenario in which, like an anti-Big Bang, everything will start contracting again towards a singularity. But I mean, I'm an astronomer and not an astrologist, so I can't look into the future. But if you assume that the properties of dark energy are not going to change and that it's really some form of cosmological constant, then that's the most likely scenario for the future.
Are there any other missions, sort of future or current, that you're particularly excited about in terms of your own research? Are you excited about what JWST might bring, or the Square Kilometre Array, for example? Or what are the big missions that you are excited about now or in the future?
So there's one big survey, it's called Euclid, that is doing something similar to what DESI's doing, but it's a space mission. So whereas DESI is ground observation. And Euclid not only measures the distribution of galaxies, so the large-scale structure, but it can also measure the lensing of light as it comes towards us. So analyzing this combination of the clustering of galaxies and the big lensing is a very powerful tool that will allow us to constrain modified gravity. So this third alternative explanation for dark energy that I mentioned. But there are also other interesting things going on. As you mentioned, SKA, that really will allow us to push even further back in time during something called the Dark Ages, where you only had neutral hydrogen, so before the first stars and things like that. So that is also very exciting. And then there are also more experiments about the cosmic microwave background. So in the past, we had experiments called WMAP and Planck. But we also have future surveys, such as it's called CMB Stage 4, for example, that really will measure the cosmic microwave background to a precision that we have never before, and also in particular measure the lensing of the cosmic microwave background. So this combination of different effects that we talked about. And then all of these different probes combined will really allow us to gain precision cosmology is what we call it. So really measuring all the different cosmological parameters to precision, to unprecedented precision.
That's amazing. Just it's sort of all coming together. I suppose it's just, cosmologists and astronomers and institutions working together to sort of solve some of the biggest questions facing us, really, isn't it?
Yeah, I mean, we only have one universe, right? Yeah. So it's not like we can just go ahead and come up with a different tabletop experiment and do it over and over again. But what we can do is we have all these different traces of the expansion of our universe and all these different things we can observe. The background radiation, the lensing, the distribution of galaxies. We can also look at clusters of galaxies and how they behave and so forth. So we have many different avenues, and really only the combination of all of these will really allow robust measurement of cosmology, because of course there are systematic effects that each individual probe suffers from. So to be really 100% sure, we need these different probes to validate each other's results. So we know for sure that, it's not a loose cable that we're observing, but actually dark energy.
Fantastic. This always happens whenever I talk to astronomers and cosmologists like yourself. It's just so inspiring and exciting, and I know I'm going to be thinking about it all for the rest of the day. But I just want to say thanks for coming on the podcast and for speaking to me and for sharing your knowledge and expertise. And good luck with your research as well. I mean, I hope you'll sort of stay in touch and let us know what you and your team find out. But I just want to say that thanks again for speaking to me today.
Well, thanks for having me. It was a pleasure. And maybe 5 years from now, you're going to get an update with exciting news.
Cool. Hope so.